this is still the plan. We talked about graphical models, the very introduction last time. Undirected models, directed models. I'm going to give you a one-slide refresher in a second. The slides for Monday and hopefully today are still online. The password is the same as before. And if you find typos or have suggestions or questions, now here's my email. Feel free to send me an email. Okay, so this is the one-slide summary. We talked about graphical models, that they are a way of representing properties of family of probability distributions graphically. So we looked at directed graph models, which usually are called belief networks or Bayesian networks, where the rule is that you want to write a big joint distribution of many variables as a product of smaller things, where the smaller things is always one variable conditioned on all the parents in the graph. And then we looked at Markov networks, which are based on undirected graphs, where we don't have to just multiply conditional probabilities together, but we can multiply arbitrary functions together. And the rule is that you can include one factor for each clique of the graph, where a clique is a fully connected subset of nodes. And the result might not necessarily be normalized, so you have to add a normalizing constant in front, which you can compute as summing over all possible values of the product. So in order to actually specify a distribution, what we have to do, we have to specify the graph that gives you the general structure, and then we also have to fill in these terms in the product with actual values. So for either the table of conditional probabilities or these potential functions, as we call them, which are just functions of one or more of the random variables. Okay, everybody remembers? Good. Because unfortunately, you can forget most about this again. Because graphical models of this type are really, really nice. Well, they're really nice if you have interpretable causal relations to model, like does smoke cause cancer, yes or no? For most of the applications where you do not have a nice mechanistic explanation of what's going on, we care less about the true distribution and how it factorizes, and we care much more about how can we build a model. How can we build a tractable thing of software in my computer that we can then use for computation. And these are built on these, but these two are not enough. So what we really want will be Effector graphs. Has anyone heard of Effector graphs? Good. So Effector graphs are based on one relatively simple observation, which is a limitation of the Markov networks that we saw before. So look at this distribution. It's a distribution of 3 random variables that's given as a product of 3 terms with 2 variables each. What's the corresponding graph in the Markov network? A triangle, exactly. What's the rule? For if we have a term that depends on 2 variables, then there must be an edge between these 2 variables, right? Because an edge is a clique of 2 variables. So we have one factor that includes AB, so there's an edge from A to B. We have a BC, so there's an edge between BC. And we have a CA, so there's also an edge between C and A. Makes a triangle. How about this one? It's a probability distribution that just has one factor, and this one factor depends on all 3. The same. It's also a triangle. Why? Because the rule is if multiple variables interact, we need a fully connected subgraph in our graph that corresponds to these variables, a clique. And if you have 3, then a clique is a triangle. So both of them have the same factorization, even though no, they have different factorizations, but they have the same graph. So that's a shortcoming of this Markov thing. Even though from a practical side it makes a difference if you have one function with 3 arguments or 3 functions with 2 arguments, the graph doesn't tell you this difference. So there's no one-to-one relation between the graph and the stuff that we would actually implement, which is functions and how we multiply them. So to make clear that this is really a problem, one thing that you can observe is that many problems have a good model in terms of few interacting things. Think of Facebook. What matters most if one person befriends another person. That's a pairwise interaction. There's always 2 partners interacting. Now imagine the world of Facebook where a random variable could be you want a potential function that checks is person A with person B a friend or not. So in the end, what you would get is a probabilistic distribution. Here I just write it with 6 people, which for every pair of people evaluates their relation to each other. So if you check that, it's a product of lots of function. Each function takes 2 arguments. If you started with the 6 variables, it's 6 chose 2 functions, 15 functions. So overall, you would have to fill in L squared value for each function 15 times. That might be a lot if you're Facebook, but it's quadratic in the number of variables. That might be doable. The corresponding graph is this. And since every variable interacts with every other, it's a fully connected graph. If you give this fully connected graph to the next person and say, here's my graphical model, they don't know what to do. They might think, oh, maybe this is a graph that has a factorization in terms of quadruples, right? Then suddenly, instead of L squared value, you would need to estimate L to the 4th values. Or maybe they think it's just one big chunk where everything is modeled together, then you would have to store L to the 6th values, all possible combinations of everybody interacting with everybody. So the graph alone is not enough. It doesn't tell us if the model is doable and tractable and practical for the computer or not. So people came up with a small extension that doesn't change the class of distribution we can represent, but it makes it much more useful for practical tasks where you sit down and write the model yourself, and these are Effector graphs. So it's a very simple trick. We augment our notation. Instead of just variables and edges, we introduce additional nodes that are so-called factor nodes, and we draw them slightly differently. We draw them as little squares instead of as open circles. And each square corresponds to the one function in your product that defines the probability distribution. So if you have a function, so this was the network we started with, a triangle. If we have a probability distribution that is defined as one function of 3 arguments, we would put one black square because we have one function, and we would connect it to all the variables that contribute. So the little square in the middle, B, is connected to all 3 variables. Okay? In the second situation where we had a product of 3 functions, each of them takes only 2 arguments. We have 3 little squares, and each of them is connected to only 2 variables. Okay? So now we have a representation where we can directly from the graph read off how many functions we have and how many arguments each function has, which is what you care about in practice. Okay? It's just a notational trick, and this is really what came out of many years of research as a really, really useful way of writing probabilistic distributions. Okay. In particular, that means different factor graphs can have different Markov networks, can have the same Markov network. B and C both lead to the triangle. And if you remember how you could specify if things were conditionally dependent or not, for that you needed the network. So both B and C would have the same conditional independent statements. But if you care about the model, then you don't care that much how much mathematically the independent statements, if they are the same or not. What you care about is if you can compute the things, and then factor graphs are a much better way of representing things. Okay, so from now on, we're just going to use factor graphs because, well, they are a good thing. This was for an undirected model. You can also do a factor graph for a directed model. These are slightly less interesting because in a directed graph, you already knew exactly how many product terms you would have and how they look like. You have one for each variable, and it's always the conditional probability of the variable given its parents. So from the directed graph, you can directly read of the factorization. If you introduce this factor graph, you don't win anything, so it's typically not used. For undirected models, it's used. Okay, so here's the definition of a factor, what a factor graph is. If you're given a function of a certain number of arguments that is written as a product of terms which have a certain number each of them has a certain number of arguments, then you draw a square for each of these product terms and a circle for each of the contributing variables that is connected to it. We already saw that. And then if you want to make that into a probabilistic distribution, you have to add your normalizing constant again. And the normalizing constant is fully determined by the function f by summing over all of its values, as we saw before. So specifying this product is enough. The normalizing constant is just a nuisance. Okay, if you looked at the graph as it was, where is it? Well, here's one. you will see that this is not a Effector graph is not an arbitrary graph, it's a so-called bipartite graph. A bipartite graph is a graph that has two different kind of vertices, and there's only ever an edge between one type of vertex and the other type of vertex. So a Effector graph is a bipartite graph where you have factor nodes and variable nodes, squares and circles, and there are only connections between factor nodes and variable nodes and backwards, but there's no connection directly from a factor to a factor, and there's no connection directly from a variable to a variable. Sometimes that can be useful to keep in mind. Okay. The good thing about factor graphs, as I said, is that they are really easy to handle in practice. So, for example, if I give you a factor graph like this, how is the corresponding probability distribution factorized? Well, you check how many terms there are. There must be 4 factors because there's 4 little squares. And then for each of them, you count which variables contribute. So for the first one, it's x1, x2. For the second one, it's x1, x2 as well. For the third one, it's x2, x3. And for the fourth one, it's just x3. And you get this kind of representation. Is that clear?
Is there a point comparing two factors for the same layer?
Sometimes it's convenient. Maybe you have information based on one source and you have information based on another source. So in practice, it doesn't hurt to do that. I mean, you could also do the trick and say, well, my FD, which is defined on only one variable, I can merge that with another one. But maybe they have the different semantics, so I want to keep them around. In theory, I can have as many of the factors I want, even if they take the same variables. Okay, so that's easy. Same thing on the other direction. If you have any kind of factor, any kind of product that defines a distribution, what's the corresponding factor graph? You count how many factor nodes you need. That's the number of terms. You count how each of them is connected to how each other one. And so this is one function of one argument, one function of another argument, one function of 3 arguments, which happens to be a conditional distribution, but for the factor graph representation, that doesn't matter. And you come up with this factor graph. All of you should have been able to do that yourself. It's just mechanical counting and connecting. So that's the good thing about it. There's no thinking involved anymore. Okay, so let me give you some examples how you would use a factor graph actually for a useful problem. Because the nice thing about factor graphs is that really it's a very canonical thing how to use them for real problems. So think of this problem. Here you have a problem of denoising. You're given an image, which is a rectangular array of values. So each pixel is a random variable. And in fact, what your output is also an image of the same size. So another set of random variables, as many as you have pixels. And now you want to be able to model the joint distribution of the noisy and the denoised image at the same time. So you want a probabilistic distribution of, if you have n pixels, it would be 2 n variables, n y x variables and n y variables. So the typical way you would set this up, you would think about, well, I have to do something to each pixel, and I have to do something maybe between neighboring pixels. So what you could come up with is a factor graph like this. You have a grid. Of course, it has to be more than 3. It's a grid as big as you have pixels. And then you have so the lower ones, did I put that there? No. So the ones that are lower and connected, this will be the y's, the denoised pixel values. And the ones above that are not connected could be the original pixels, the noisy ones. And then, based on this factor graph, you would know which terms you have to multiply with each other, or vice versa. If you first come up with the terms you want to multiply, this would be the corresponding factor graph. And what you will get is a probability distribution, a joint distribution of inputs and outputs, x, y, which is a big product, and we write it in this Gibbs form as exponential of minus an energy function with a normalizing constant in front. And the energy function is now the sum of the individual contributions of the factors, right, because of this exponential form. And there you have exactly one term per factor. And you have some factors which look at one input and one output at the time. So these vertical ones, they look at one denoised pixel and one noisy pixel at a time. It's these ones. And you have one set of factors which look at two of the denoised pixels at the same time. That's these ones. And now all you have to do in order to specify distribution is actually assign values to these. So if you think of the x and y as integer valued gray intensity values, for example, you can say, well, my first design choice is I set these interactions between noisy and denoised version of pixels as the difference of their intensity squared, something people do. And to the interaction between two neighboring pixels as the absolute value between them. I could also do something else, but it's a popular choice. And these have some kind of interpretation, right? So in order to make a configuration likely, that means the probability for any kind of assignment of pixel values should be high. That means by this formula, the energy should be low. So when is this energy low? Well, when if the individual terms are low. So these guys should be low and these guys should be low, then it's a very likely configuration. So what does that mean? That means the first ones are small when the outputs are similar to the inputs. The difference is small. Makes sense? If you denoise an image, you don't want to assign arbitrary values. You want to assign something that is close to the original image. And these ones will be small if two outputs that are next to each other in the pixel grid have a small difference. And that means there will no be like wiggly jumps in the intensity, but the jumps should be constant or slowly changing only. So you will get a smooth output. Whereas in the noisy image, you have a lot of black to white transitions. In the likely output, you will not have these kind of output transitions. So this is given, based on our prior knowledge, we just assign these values. Maybe you have some free constant like alpha beta here, but this would be a typical design step. I design my energy function in a certain way, and then I put it into my probability distribution, and then I throw the tools of graphical models that we'll hear about later today on it. This is not the best function for denoising, but it's one of the simplest, and it works remarkably well. This is the pose example. We start at the very, very beginning saying, well, how do we model a pose? We want a term that tells you how likely is it that a phase occurs at a certain location, and we want that body parts interact with each other in a reasonable way, so that body parts kind of float around arbitrarily because they are attached to each other. This is a Effector graph that expresses exactly that. It models a conditional distribution, so we have the x here as a shaded node, and you can basically forget that it's a random variable. You just think of it as some input to my functions. And then you have two types of factors. Some factors which connect an unknown location of an object part here of the head with the image, with the input image, and some which connect the location of two body parts to each other. You combine these again into an energy function which defines a probability distribution. There will be a sum over terms. The sum contains all the factors. Some of the factors are one body part with the image information. One is two body parts together. And now we have to assign reasonable values to these for all different configurations. And this is exactly what we started with in the beginning. So the factors that only look at the position, like one label variable at a time, they will be some kind of measure of appearance. Does this region specified by my labeling, location, rotation, and so on, does this look like a head, yes or no? Or how much does it look like a head? Whereas the other ones that look at two labels, like two body parts at a time, these will be the geometric constraints that we introduced, where we said, well, the head should not be floating around far away from the torso. So we introduce a term that says if the head is above the torso and not too far away, then the energy is low. That makes it a likely configuration. If the distance is really far away, then it's a very unlikely configuration. So you can sit down, you can write down expressions that express what you think is a good penalty or penalization of the head being too far away. You plug that into your terms. You've put it into the energy function, you have defined yourself a graphical model, Effector graph, and that defines a probability distribution, and you can use all kind of tools later. Okay? There was no question so far. That's not good. One question. Otherwise, I start asking questions. I have a question. Do you want another example? Okay, final example. I include it because it's really, really famous. It's the so-called Ising model. It's a model, it's again a conditional model, but the conditioning is not the important part. The important part is it's a probability of some outputs y, and these outputs y are binary labels. In physics, they are the spin of a magnet. Here, they are indicator variables. Is it the foreground region or the background region in the image? So we're trying to do image segmentation. Some pixel we want to assign foreground, some pixels we want to assign background. Since it's an image, it's again a good idea to make this kind of grid for my Effector graph. So for every possible output y, I have a white node, which is the ones that for which we want to construct a probability distribution. And then we also happen to have some x's which are observed, so we do not treat them as random variables. We just treat them as input to our function here. Okay, what do we get? We get a distribution that up to normalization factor is the exponential of the energy. The energy, again, is a sum of terms where there's exactly one term per factor. It's exactly the same pattern every time. Once we have specified this grid, the rest is mechanical. So it has to be one term that looks at the output and, at that location, and additional information from the image, if we like. And there will be as many terms as there's neighboring relations between the grids, which looks at two output variables at a time. So two foreground, background labels, which are next to each other. And now the most famous Ising model for image segmentation says, define these terms for the energy function, define these factors, potentials, and they're going to be defined as if you have a single location at a time, then the probability of having a 1, which means foreground, not the probability, the value, the energy value of foreground at that location, it will depend on the pixel value. If the pixel value looks like a horse, like it's brown, then the energy will be low. If the pixel does not look like a horse, the energy will be high. So, and since the probability will be exponential of minus the energy, that means brown pixels are likely to be foreground, non-brown pixels are likely to be background. And then we have a second term. So if we only had these things, then basically every brown pixel would be foreground, every not brown pixel would be background, and we just have to go through all pixels and check individually. But we also have the second term that looks at two neighboring labels at a time, and that will be low if they are the same, and it will be high if they are not the same. So that means foreground pixels tend to be next to foreground pixels, background pixels tend to be next to background pixels, and that will again make combinations of labels more likely if they have smooth, large regions of homogeneous labels. So you will not get regions where it's like foreground, background, foreground, background, foreground, background. That would be too many neighbors that have different labels, so that would give you a low probability. Instead, it will give you large regions where the label doesn't change. And you will get outputs that look similar to this. So there is, of course, switches, but relatively few. Yes.
And it's smaller than x meter.
Sorry?
Second.
This one? Or that one?
If x near zero, I is low, when x are.
These are so y's, right? These are the outputs that we want to produce, and low energy means high probability. And it's just that they are the same. So if you have one location and another location, if they are both background, that's fine. Background and background co-occur together. If they are both foreground, that's also fine. Foreground and foreground co-occur. But that you switch from background to foreground or from foreground to background, that means you have like an edge in your segmentation, and that should be rare. So it's an unlikely combination. For this guy, these factors have no axis, and you can see that in the graph, right? There's a white node, which is a y, and another white node, which is also a y, connected to each other. That means only these two contribute. The x was the shaded one on top, and these are only connected to the first kind of terms. I mean, this is your modeling choice, right? You can do anything you want. It's just that this happens to be the famous Ising model for, I mean, in physics, this is a probability of a certain material that spins arrange each other in one or the other direction. And you have interaction between spins, and you have an external field that pushes some parts in some directions. So this is exactly the same model from physics, but it's applied to segmenting images, and you end up with the same expression for probabilities and so on. Okay, so what should be clear is that it's not obvious how you would choose these functions at the bottom. That is really, I mean, art, and we'll see that we typically don't choose them by hand. We would learn them from training data. But what should also be clear is that the structure, which terms occur, this is completely determined by the Effector Graph and vice versa. If I know which term I want to have, I know the Effector Graph. If I know the Effector Graph, I know which kind of terms there will be. Not the exact values, but their functional shape. Okay? Okay, so this is the summary then. Graphical models represent distributions. We already saw that. We saw directed, undirected models. Now we also saw Effector Graphs that are very explicit in which functions are multiplied together in order to build a distribution. Doesn't change the class of distribution, just changes them. It's a more convenient way of writing. Whenever you think about undirected graph and you want to build one yourself, thinking in Effector Graphs is a good idea. Then to actually fill the distribution with values, we have to specify what these functions are that are multiplied together. And for the undirected models and Effector Graphs, these are these potential functions, which more or less ad hoc appeared on the previous slide. And that is because typically you do not specify them, you learn them from data. Whereas the graph structure is something you design manually. It's your domain knowledge that pixels interact if they're close to each other, but pixels that are really far apart from each other, you would not put a term. These don't interact. So this is your knowledge. The actual values you would then learn from data. And that's the second part now. Okay. So this is a figure I took from the book of Bishop, I think. Well, it's one of the figures in one of the books. And it shows you the zoo of what graphical models have been developed and how they all interact with each other. So there is the big field of graphical models, and we've only looked at very, very few of them, right? We looked down there on directed graphs, and then as a special case, Effector Graphs. We looked to the right to directed graphs, Bayesian networks, and then it gets too small to read. But we've only scratched the surface of graphical models. There is a lot more, both in terms of theory, but also in terms of actual practical applications. Okay, so what I want to jump to now is learning from data. So now that we've fixed our structure, we know exactly what kind of interacting terms we have. We want to know which values do we have to put into this distribution to make it a good distribution that describes my problem well. And this is usually not possible by just sitting down and thinking hard. Maybe in this causal example of Sherlock Holmes, fine. But if the problem is image segmentation, I do not know how to write down and write the right energies and right factors, I mean, in terms of numeric values. Should it be 0.5 or 0.6? I mean, who knows? So instead, what we're going to do is we're going to learn these automatically from data. And for that, of course, we first need data. So we assume that we are given a set of examples that are samples from the distribution we care about in the real world. So these are not samples from our model, because we don't have a model yet. This is data that comes to us from some process, and we want to find a model that approximates the real unknown model as well as possible. So we want to do probability estimation, where we are given some kind of model class, we fixed our structures, we just want to fill in the values. And then we want to identify one specific choice of functions, of function values, in order to fit the data that we observe from the real world. The general assumption is that the training data we get is sampled independently from this and identically distributed from one distribution. So it's just identical samples that have no dependence between them that makes the analysis much easier. You can also learn from dependent data, but that's a different topic. Okay, so the easiest example, yes? If you want to do supervised learning with inputs and outputs, yes. So here, for now, it's just data, and you want to fit a model of the data. It can be input-output pairs, or it can be just anything. So the easiest example to go through is coin tosses, and then there is just one variable, which is the outcome of the coin toss. I mean, the method works for both. Okay, yes. So the easiest trivial example is coin tosses. You have a random variable that is the outcome of your coin flip. Your coin that you flip has a certain internal probability of landing on either heads or tails. And then you repeat that a couple of times. That gives you observations xi, and each xi is either head or tails. And then what's the true probability of the coin to show either heads or tails? Simplest possible example from kindergarten or high school. Well, we write down the probability. We give it a name, so we say that there's a parameter theta head, which is the probability of showing head, and there's theta tail, which is the probability of showing tail. And then, in fact, one of these two would be enough because they add up to 1. Yes?
What data means?
It's just a short way of writing for this is the quantity we care about. So it's an unknown quantity. We don't know what the true probability of heads or tails is, but it's what we care about. Essentially, it's a parameter we want to estimate, but the parameter comes on the next. Okay? So what's the standard way that you learn in school? Well, you count how often the event of interest happened, and then you divide by the total number, right? So if you flip the coin 100 times and 59 times you got head, then your probability estimate would be 59 over 100, so 59%. So I will write this as an estimate. So given the data that we observe, we can estimate a value. The true value would be theta head. That's the true probability of the coin showing head every time. We will not be able to compute exactly the true one, but we will be able to estimate it. And the estimate I indicate with this little hat. That means is an estimate of the thing we actually care about. And we can write it as well, the number of outcomes of head divided by the total number. And I will often use this notation with Iverson brackets, where I write a summation, on averaging here, of some condition, and then if the condition is true, it counts as a 1, and if the condition is not true, it counts as a 0. So the notation here means sum over all over all coins, over all data points that you observe. Whenever it shows head, you count a 1. When it doesn't, it counts a 0. So in the end, you get exactly this ratio that you care about. So this is the easiest way from kindergarten, right? Just count and divide. Yes, and this notation of head will go through the lecture as our estimate based on data of the quantity we really care about. The next example you also learn from school is Gaussians. So imagine you have a random variable which you know is Gaussian. Maybe it's, whatever is Gaussian in the world, the height of or length of some animal or something like that. You know it's a Gaussian distribution. So it has this parametric form. And the only thing you don't know is what is the mean and what is the standard deviation, or the variance. Standard method from school, you compute an estimator for the mean by just taking your data and averaging it. And then you also compute an estimate of the variance by taking, for every data point, you subtract the mean. That gives you a residual. You square the residual, sum it up, or average up over all data points. That gives you a standard estimate for the variance. Why do you do that? Because your teacher told you so. Right? Okay, so your teacher told you so is usually not a good reason in life. So we need it's a very good reason in life, but it's not the only reason for many things. So we need a more general principle. How can we, given data, how can we estimate a probability distribution? So here, by setting theta and sigma squared to something, we got a probability distribution, right? And the general principle that is the easiest to think about is maximum likelihood. So there's a lot of possible Gaussian distributions out there. So, for example, if we think Gaussian, then every Gaussian distribution out there will have the form a normalizing constant times exponential of minus the squared difference divided by the variance. This has two parameters. We put them into theta. So the mu and the sigma square, we say these are the unknown parameters that we care about. For different models, we will have different parameters that we want to estimate. For the coin toss, the easiest is to just make each unknown. So you have a probability table with all different outcomes. You just make each entry of the probability table into an unknown parameter. So for the coin toss, you have two parameters, the head and the tail. Again, one of them would be enough. You can also keep both, doesn't matter. Okay, so maximum likelihood means out of all of these parametric distributions, so you have the choice to set sigma and mu arbitrarily, or you set, in general, your theta arbitrarily. Which ones should you use given some data? Use the one that makes your observations most likely. So under each of the model, there's a certain probability that you see this or that. So choose the model such that the probability of that what you actually saw is the most likely one. Okay? So if you have one model that predicts heads should never appear and everything should be tails, and the other set 59%, 60%, choose the one that is closer to the one that you actually observe. So mathematically, that means you define, if your unknown quantity is theta, you define an estimator of theta. We call it the maximum likelihood estimator, so we give it a little index ML. And we say, define the likelihood of your data. That's the probability of your data under the model which has parameter theta. So I write that as P of D, where D stands for data, with parameter theta. And that is just the product of the probability of each individual outcome. That gives you a function which only depends on theta. The data is fixed, right? It's observed, we have it, but it's still, the theta is an unknown quantity. So this is a function of theta. And now we can check for all possible values of theta, which one gives this the highest likelihood, and that's the one we call the maximum likelihood estimator. So choose the value that makes the observations most likely. As often, there's different equivalent ways to express this, and the maximum likelihood estimator, so the one that maximizes the data likelihood, is also equivalent to the maximizer of the logarithm of the likelihood, just because, well, the point that the logarithm is a monotonic function, so if something maximizes a function, it also maximizes the logarithm of the function. That's equivalent. And sometimes it's more convenient not to talk about the logarithm of the likelihood, but about the negative of the logarithm of the likelihood. And then, of course, we don't have to maximize it anymore, we have to minimize it. These are all mathematically completely identical. It's just sometimes one gives you easier expressions than the other. Or it's numerically more stable, that can also happen. For the product over many terms, if you have small terms, the product quickly goes to 0, whereas the other one is a sum that doesn't behave that bad in terms of floating point and so on. Okay, so let's look at maximum likelihood. Is it a good idea? What is the maximum likelihood estimate for a coin toss? So we have the same situation as before. We have a coin. It has a certain probability of actually landing on heads or on tails. And all we need to know, and this is given by the parameter theta, the true parameter theta. So what estimate do we get for it? Well, we have to write down what's the probability of our data for the model that we want to estimate. So that is the probability of getting a 1 or a 0, where 1 corresponds to head now and 0 corresponds to tail. So the probability of seeing a 1 is, both of them are given by this expression. It's a convenient way of writing. Seeing a 1 has probability theta. Seeing a 0 has probability 1 minus theta. So if you check, your x can only be 1 or 0. So if it's 1, then the first term becomes theta, and the second term becomes, 1, because it's something to the 0. And if the x was 0, then the first term in this product becomes 1, and the second becomes 1 minus theta. So this is just a convenient way of writing that it's either one or the other, depending on what your x was. Okay? So what is our likelihood? Well, it's the product of all of these over the data that we observed. And if we use the logarithm of the likelihood, then it's the sum of the logarithms of these things. So we can take the logarithm of this. We know how to take logarithm of exponents and so on. And in the end, what we will get out is an expression that is the logarithm of this ratio theta over 1 minus theta multiplied with the sum of the observations minus another term, which is n times logarithm of 1 minus theta, which is not anything that, I mean, it's obvious, but that's what comes out when you just multiply them out. And if we think of this just as a function of theta, because the x's are fixed anyway, then this is a smooth, nice, convex function, and we can actually find its minimum numerically, or by just computing its gradient or derivative here and setting the derivative to 0. So if we take this log likelihood and we set its derivative to 0, we get this expression here. Well, this is the derivative. If we set it to 0, this equation must hold. So in the end, what we get out is that the maximum likelihood estimate is, well, 1 over the sum of the xi's, where the xi was 1 if it's heads and 0 if it was tails. So count how often heads occurred, divide by the total number. You've seen that before. So the maximum likelihood estimate for coin toss is exactly the same as the standard solution. And, well, that's just because it's a good idea to do. So that's why you teach it in school, because maximum likelihood estimation is a good thing. Questions?
There should be plus and then minus.
Where?
Where minus n logarithm of 1 minus and
Yes, okay. I might have computed the negative of the L here instead of the positive. You're right. It's not that? Did I mess up the signs? Good. Thank you. I messed up the signs. I'll try to fix it. If you remind me or send me an email, I'll fix it. Otherwise, I'll forget. Some expression comes out. If you take the derivative, you will get the rule of counting and dividing. Okay, next example we had is Gaussian. What happens for the Gaussian? You assume that the true distribution of your data would be a Gaussian. Could be. It would have some parameters theta, which is at least the mean and the standard deviation, or variance here, which means every data point that we observe has the probability 1 over, the usual Gaussian expression for the probability. We can compute the logarithm of that and sum it over all possible data points. And again, I took the negative logarithm here. Sorry about that. And what we get is it's the sum of the negative of the exponents plus the sum of the logarithm of these guys, which hopefully is this, up to sign errors. Again, the data is fixed. This is just a function of the parameter. So we can take the derivative with respect to the parameters, and where they are 0, we will have the minimizer in this case. So let's do that. If we take the derivative of this guy with respect to the unknown mu, we will see that what we get is your best estimate for mu is 1 over n, the sum of the data points that you observed. So again, this is exactly this thing that we learned in school. For the Gaussian as well, the maximum likelihood is the typical solution. The same trick works if you do it for the standard deviation, but I didn't want to do the math. I have too many sign errors in my math. Okay, so this just means that maximum likelihood is everywhere, and we might not call it that, but it lies behind a lot of things we do. If we estimate a quantity from observations, it's commonly a maximum likelihood estimator. I mean, it's a good thing. Okay, there's another explanation why maximum likelihood is a good idea, and for that, it's about approximating one distribution by another distribution. So if you want to know if one probability distribution is similar to another probability distribution, then typically what you use is the Kullback-Leibler divergence measure. You might have seen that in a probability class. If you haven't seen it, believe me that it's defined this way. You take the logarithm, you take the ratio of the two distributions, or of the density if they have a density. Then you take the logarithm of that, and then you take the expectation with respect to the first of the two distributions, which means you sum over all values multiplied with the probability of that value actually occurring. It's not properly a distance, it's not symmetric, it doesn't fulfill the triangle equality, but it is a measure of similarity that is large if the two distributions are very different, and that is small if they are the same. So what can we do in order to use this for parameter estimation? Well, since we try to estimate a probability distribution, and we are given to us is data, and from the data we can also define a probability distribution. We can just take the empirical distribution, meaning it's the sum of delta peaks where there's a delta peak at every value you observe divided by the number of samples. So we define the empirical distribution, I call it Q here, which is once by what we observe, zeros elsewhere. For the discrete case, for the continuous case, it would be a delta peak, but let's not go there. So then we can write down what is the distribution, the parametric distribution for which we only want to know the parameter theta, such that it's as similar as possible to the observed data distribution. So that means we have to minimize the difference, the distance between the two, the KL divergence, between the empirical data distribution and the model distribution for which we don't know the parameters. And we minimize that over all possible parameters. We plug it into the expressions. This is the sum of these weighted logarithm ratios. When you have a logarithm of a ratio, you can decompose it into two parts. You observe that the first of these two, Q log Q, that's the entropy of Q, negative, but it doesn't depend on theta at all. So the minimizer of this difference of expression will be the same as just the minimizer of the second one, the Q log P. So that is the same as the maximizer of the negative. So we also get that this is the maximum of the sum over the Q times logarithm of P, which still depends on our theta. And now we know that the Q is our empirical distribution. So it's either 1, or rather 1 over n, or it's 0 at all possible values. And it's only 1 over n at a value that occurred, and it's 0 everywhere else. So this sum over all possible x's turns into a sum over just the observations that we made, 1 over n for each of them. So we end up with the sum of the logarithm of the probability with the weight 1 over n in front. What is that? That is the logarithm of the likelihood. It's exactly the same expression as what we started with before. And that means we have to maximize the likelihood of the data in order to get the difference between the distributions as small as possible. So maximum likelihood estimation is also the same as finding a parameter that approximates the model distribution as closely as possible to the observed distribution, the empirical observed distribution. So it's still a good idea to do maximum likelihood. Okay, I think I'll make a break here, and then we'll talk a little bit about what does it mean that an estimate is good or bad, because so far I just showed you that we can estimate it, but there's no guarantees that this is a good idea to use. So let's make a break of